Hey everyone, and welcome. Here at TalkTensors, we're always hunting for the next big thing in AI. And today, we are diving into a paper that has been making some serious waves. It's called Mamba, and it's proposing a totally new blueprint for sequence modeling that, honestly, could change everything. Let's get right into it. Look, for years now, the transformer has been the undisputed king. It's the engine behind pretty much every large language model you've ever heard of or used. But for all its power, it has a fundamental problem, a kind of architectural flaw that's really starting to look like a major roadblock for where AI needs to go next. So let's talk about that problem. We're calling it the transformer's dilemma, because it turns out its greatest strength is also its biggest weakness. The very thing that makes it so incredibly powerful also makes it unbelievably expensive and inefficient, especially as our ambitions get bigger and bigger. The secret sauce for the transformer is this mechanism called self-attention. It's what allows the model to look at an entire sentence, or heck, a whole document, all at the same time. Every single word gets compared to every other word, which lets it grasp these incredibly complex relationships and all the nuances of context. It's exactly why it's so good at understanding language. But here's where the problem really hits home. Because every single piece of information has to be compared to every other piece, the computation doesn't just grow, it explodes. It grows quadratically. So if you double the length of the text, you don't just double the work, you quadruple it. And that just becomes a computational nightmare when you want to process entire books, or high-res audio, or even a full human genome. And this creates a huge bottleneck. I mean, for short sequences, transformers are fantastic, no question. But for the really long sequences that are key to the next frontier of AI, we're talking analyzing a patient's entire medical history or a full-length movie. They just become painfully slow, outrageously expensive, and they need a staggering amount of memory just to keep track of all those comparisons. Now, this scaling issue, it's not some new discovery. For years, researchers have been on this quest to find a more efficient way to handle long sequences, and it's led to a really fascinating history of different ideas and approaches. So let's just do a quick walk through that history. We started way back with recurrent neural networks, or RNNs. They were efficient, processing one thing at a time, but they were also kind of forgetful. They struggled to remember things from way back at the beginning of a sequence. Then you had convolutional neural networks, CNNs, which were fast, but could only really see small local pieces of the data. And then came the early state space models, or SSMs, which were also super fast, but really had a hard time with dense stuff like human language. And that right there was the Achilles heel for all of these earlier attempts. They were efficient, sure, but they were missing what we call content-based reasoning. They couldn't, on the fly, decide which parts of the input were important and which parts were just noise. They pretty much treated all information as being created equal. And this is where Mamba enters the chat. It's a completely new kind of state space model that introduces a really game-changing idea. A kind of selective memory that lets it reason like a transformer, but with the speed and efficiency of an RNN. Okay, so the official name for this is a selective state space model. In plain English, what this means is that the model's own rules aren't set in stone. They actually change depending on the data it's looking at. So for every single piece of information it reads, Mamba gets to decide, should I keep this in my memory or should I just forget it? This quote from the paper really nails it. Think of it this way. A transformer's memory is like trying to remember a lecture by writing down every single word the professor says. It's massive and just totally unwieldy. Mamba, on the other hand, is like creating a smart summary. It listens to the lecture and only jots down the most important points, compressing all that context into a tiny, super efficient state. So how does it actually pull this off? Well, imagine a conveyor belt of information flowing by. As each piece passes, Mamba's selection mechanism acts like a super smart sorter. It looks at the token, and based on what it is, it decides whether to add it to its compressed memory bank, or just let it go. This builds up a highly relevant, compact state that it can then use to make incredibly accurate predictions. And that's the secret sauce. That selectivity is exactly what lets Mamba absolutely crush tasks that were impossible for older models. A great example is the selective copying task, where it has to find and remember very specific pieces of information from a super long sequence while ignoring all the useless filler in between.
Okay, so the theory sounds incredible, right? It's elegant, but does it actually hold up in the real world? Well, the researchers put Mamba through its paces across a whole bunch of different areas, and the results are frankly stunning.
First up, language. So on this slide, you're seeing a 2.8 billion parameter Mamba model going head-to-head with a transformer of the exact same size, in this case Pythia. Now, not only does Mamba get a higher accuracy score, but look closer. It actually outperforms a transformer that is more than twice its size. I mean, that is a massive leap in what you can get for the same amount of compute. Now let's jump to a field with truly mind-bogglingly long sequences, genomics. This chart shows perplexity. It's just a measure of how well a model predicts what's coming next, and lower is better here. As you can see, Mamba's line just dives down much more steeply than its competitors as the models get bigger. It is simply better at learning from the incredibly long and complex patterns you find in DNA. And it's not a one-trick pony either. This isn't just about text and DNA. This chart kind of sums it all up. Mamba is hitting top-tier, state-of-the-art performance across language, genomics, and even raw audio generation. And, as if that wasn't enough, it's doing it all with a staggering 5 times faster inference speed than a comparable transformer. Let's just pause on that number for a second. 5 times higher throughput. This isn't just some cool academic finding. This is a total game changer for real-world applications. It means AI tools that are cheaper to run, that are way more responsive, and that can finally be used in places where transformers are just too slow or too expensive to even consider today. So when you put all this evidence together, it really points to one conclusion. Mamba isn't just some small incremental improvement. It represents a potential new foundation for how we build these models, one built from the ground up on linear time efficiency. So what does this all add up to? Why does Mamba matter so much? Well, first, that linear scaling. It finally unlocks the ability to model sequences with millions of tokens. We're talking about processing entire code bases, analyzing full medical research libraries, or understanding hours of raw audio in one pass. It's also designed to be super efficient on modern GPUs, which makes it practical. The architecture itself is cleaner, and maybe most importantly, it has proven itself to be a true general-purpose backbone, getting incredible results on completely different kinds of data. You know, the authors themselves put it perfectly in their conclusion. Our results suggest that Mamba is a strong candidate to be a general sequence model backbone. That's a bold statement, but based on the data, it's a well-earned one. And that leaves all of us with one massive, provocative question. For years, the story of AI has really been the story of the transformer. But now, with Mamba's incredible blend of performance and efficiency, we really have to ask, could this be the architecture that finally moves us past attention and powers the next generation of foundation models? This is for entertainment purposes only.